In the spring of 1912, a peculiar object occupied the center of a London workshop floor. It wasn't beautiful in any conventional sense. A mass of steel components, canvas belting mechanisms, and most conspicuously, a cylindrical water jacket wrapped around what appeared to be a rifle barrel. The Vickers machine gun existed as a physical object, but its true nature remained to be proven through operation rather than observation. Hiram Maxim stood in that workshop surrounded by the accumulated evidence of a decade's worth of theoretical refinements. The original Maxim gun of the 1880s had proven the concept of automatic discharge through recoil operation, but that design carried inherent limitations. It was heavy, complex, and required frequent maintenance during extended operational sessions. The authorities of the era had accepted automatic hardware as inevitable, but they demanded something more refined, a system that could operate continuously without the cascade of failures that plagued earlier designs. What made this moment significant wasn't the device itself, but the engineering philosophy it represented. Maxim had approached the problem from a thermodynamic perspective, rather than a purely mechanical one. Every automatic system generates heat as a byproduct of energy release and friction. Previous designers had treated this heat as an inconvenience to be managed through pauses or rapid component changes. Maxim recognized it as the central constraint around which all other systems must be designed. The water jacket wasn't an afterthought, it was the foundation. By surrounding the barrel with a controlled volume of water, Maxim created a thermal buffer capable of absorbing enormous quantities of heat energy. But water cooling introduced its own complications. The system needed to circulate water efficiently, prevent steam pressure from damaging the jacket, and maintain consistent temperature distribution along the entire barrel length. Each of these requirements demanded careful engineering of components that had to work in harmony under extreme conditions. The toggle lock mechanism represented another departure from conventional design thinking. Most recoil-operated systems use some variation of a tilting bolt or rotating lock. Maxim's toggle lock, refined through years of testing, distributed mechanical forces along angular surfaces that naturally absorbed stress while providing positive lockup during operation. When the barrel and bolt recoiled together, the toggle remained locked until the components traveled a precise distance. At that exact moment, the toggle's geometry forced it to break upward, unlocking the action and allowing the extraction cycle to begin. This synchronization between thermal management and mechanical operation defined the Vickers design philosophy. The device didn't simply operate automatically, it maintained that operation through the integration of cooling, recoil mechanics, and ammunition feed systems that had to function as a unified whole. The canvas belt feeding the mechanism couldn't jam, the water couldn't boil away too quickly, the toggle lock couldn't fail under thermal expansion. Every component represented a solution to multiple engineering constraints simultaneously. If stories like this help you see how engineering quietly shaped history, tell us in the comments what surprised you so far, and stay with us for the next chapter. Maxim's path to the 1912 refinement began not with hardware, but with fundamental questions about energy conversion. His earlier career had focused on electrical systems and mechanical devices, where efficiency and reliability determined commercial success. When he first examined automatic mechanisms in the 1880s, he approached them not as a specialized tactician, but as an engineer analyzing inefficient machines. The breakthrough insight came from recognizing that every triggered event released energy in multiple forms: forward propulsion, rearward recoil, thermal energy, and acoustic pressure waves. Most designers focused exclusively on the forward trajectory. Maxim saw an entire system of energy flows, most of which were being wasted or ignored. If recoil energy could be harnessed to operate the mechanism, the operator wouldn't need to manually cycle the action for each sequence. The original Maxim gun proved this concept, but it also revealed the limitations of first-generation thinking. The device worked, but it was temperamental. Sustained use generated heat that affected metallurgical properties of the barrel and receiver. Ammunition belts occasionally jammed when the mechanism's timing fell out of synchronization. Water in the cooling jacket sometimes boiled away before crews could replenish it, leading to catastrophic overheating. By 1912, Maxim faced a different kind of pressure. The device needed to transition from promising prototype to reliable standard equipment. Procurement committees were demanding specific performance metrics, sustained operational rates measured in hundreds of cycles per minute, operational periods measured in hours rather than minutes, and reliability percentages approaching industrial machinery standards. These weren't suggestions, they were requirements for any system that would receive production contracts. The challenge lay in understanding why previous designs had failed under extended operation. Maxim assembled data from field tests, analyzing every reported malfunction, every maintenance issue, and every operator complaint. Patterns emerged. Most failures occurred after sustained periods when thermal expansion began affecting component tolerances. The toggle lock in particular showed sensitivity to temperature variations. At room temperature, clearances and timing were perfect. After several hundred cycles, thermal expansion in the receiver altered these relationships enough to cause intermittent failures. This realization forced a fundamental redesign of the toggle lock's geometry. The joint needed to maintain precise timing across a temperature range spanning hundreds of degrees. Maxim experimented with different angles, different surface treatments, and different materials. Each variant underwent exhaustive testing, measuring not just whether it worked, but how it worked across the entire operational envelope. The water jacket system also required refinement. Earlier versions had simply surrounded the barrel with water, assuming convection would distribute cooling evenly. Testing revealed that water immediately adjacent to the hottest portions of the barrel could reach boiling point, while water in other areas remained relatively cool. This uneven cooling created stress concentrations that could damage the barrel over time. The solution involved internal baffles that forced water circulation, ensuring more uniform temperature distribution. These refinements occurred incrementally, each building on insights from the previous iteration. By 1912, the Vickers represented not a sudden invention, but the culmination of systematic problem-solving applied to thermodynamic and mechanical constraints that had previously seemed incompatible. Understanding how the Vickers operates requires examining the device as a system of interdependent mechanisms rather than isolated components. The cycle begins with a loaded unit positioned in the chamber, the toggle lock in its fully closed position, and water circulating through the jacket surrounding the barrel. When the trigger is activated, the internal pin initiates the process. As expanding gases accelerate the projectile down the barrel, these same gases exert rearward pressure, which in turn pushes against the bolt face. In most designs, this rearward force is absorbed by a locked mechanism, while the barrel remains stationary. The Vickers operates differently. The barrel and bolt assembly recoil together as a unit. This shared recoil distributes forces across a larger mass, reducing peak stress on any single component. The barrel and bolt travel rearward approximately half an inch before the toggle lock mechanism is activated. During this initial movement, the toggle remains locked, maintaining a gas-tight seal. The toggle consists of two arms joined at an angle with the apex pointing downward. As the barrel reaches its maximum rearward position, a carefully positioned cam surface contacts the toggle's apex. This contact forces the toggle to break upward, folding the two arms into a straight line. This geometric change unlocks the action, allowing the bolt to continue rearward while the barrel is arrested and begins its return journey forward. The bolt's continued rearward motion extracts the spent casing from the chamber. An ejection port allows the empty casing to exit the receiver as the bolt reaches its maximum rearward position. Meanwhile, the ammunition feed mechanism has advanced the canvas belt by one position, aligning a fresh unit with the chamber. As the bolt begins its forward motion under spring pressure, it strips the new unit from the belt and guides it into the chamber. The barrel, which has been returning forward independently, meets the bolt just as the unit is fully chambered. The toggle lock, forced back into its angular locked position by the convergence of barrel and bolt, creates a secure seal. This entire cycle occurs in a fraction of a second. The Vickers can repeat this cycle 500 times per minute, sustained for hours. The critical insight is that timing determines everything. If the toggle breaks too early, the bolt unlocks while chamber pressure is still dangerously high. Too late, and the extractor must overcome excessive friction from the expanded casing. The water jacket's role becomes clear during sustained operation. Each cycle generates thermal energy that radiates into the barrel's steel. Without cooling, this accumulated heat would raise the temperature beyond its metallurgical limits within minutes. Water in the jacket absorbs this thermal energy through direct contact with the barrel's exterior surface. The water's high specific heat capacity allows it to absorb substantial energy before reaching boiling point. As water temperature rises, it converts to steam. Early designs vented this steam to the atmosphere, requiring constant water replenishment. Maxim's refinement included a condensation system, a separate canister where steam cooled back to liquid water, which gravity fed back into the jacket. This closed-loop system dramatically reduced water consumption, enabling truly sustained operation. Do you think this design choice was inevitable or a risky gamble at the time? Share your view in the comments and pass this story to someone who enjoys understanding how things really work. The theoretical elegance of the Vickers design meant nothing until it proved itself through exhaustive testing. Maxim established protocols that simulated the most extreme conditions, sustained operation until water supplies were exhausted, functioning in freezing temperatures, exposure to dust and debris, and cycling through thousands of rounds without maintenance. The first comprehensive test session revealed an unexpected problem. After approximately 3,000 cycles of continuous operation, the device would occasionally experience a failure to extract. Investigation showed that the extractor claw, while adequately strong for normal operation, couldn't maintain sufficient grip when casings expanded from excessive chamber heat. The problem wasn't the water cooling system, it was working exactly as designed. The issue was that the brass material, when heated beyond specific temperatures, became more malleable and would occasionally stick in the chamber despite normal forces. Maxim faced a choice: redesign the extractor for increased grip force or modify the water jacket to provide more aggressive cooling specifically at the chamber area. Both approaches had merit, but they represented different engineering philosophies. Increasing extractor force meant adding mechanical stress to other components. Improving chamber cooling meant complicating the water circulation system. The solution emerged from careful observation of thermal patterns along the barrel. Using temperature-sensitive paints, engineers mapped how heat distributed itself during sustained operation. They discovered that the forward portion of the barrel generated less heat than the chamber area where combustion gases reached their highest temperature and pressure. By modifying the water jacket's internal structure to direct more water circulation past the chamber while allowing less flow toward the end of the barrel, the system achieved more efficient cooling where it mattered most. This modification required precision manufacturing. The jacket's interior needed welded baffles positioned at exact locations to create the desired flow pattern. These baffles couldn't obstruct circulation entirely. Water still needed to reach all areas of the barrel, but they had to preferentially direct more volume past the chamber. Manufacturing these baffles consistently across production units demanded tight tolerances and quality control procedures that were sophisticated for 1912 industrial capabilities. Testing resumed with the modified water jackets. The extraction failures disappeared, but now a different pattern emerged. After approximately 5,000 cycles, the toggle lock occasionally failed to fully seat into its locked position. Inspection revealed that the cam surface responsible for breaking the toggle open was experiencing accelerated wear. The contact area between cam and toggle was small, concentrating enormous forces during each cycle. Under sustained operation, this localized stress caused microscopic metal fatigue. The cam surface required hardening through heat treatment, but this introduced new complications. Hardened steel is brittle. Excessively hard cam surfaces could shatter under impact. The solution involved a graduated hardening process that created a hard outer surface while maintaining tougher, more resilient metal underneath. This metallurgical approach worked, but it required careful control of heating and cooling rates during manufacturing. Each problem solved revealed another constraint that hadn't been apparent in theoretical design work. The canvas ammunition belts needed specific weave patterns to resist wear while maintaining flexibility. The feed components that advanced the belt required spring tension calibrated within narrow ranges. Water jacket gaskets needed materials that could seal effectively across extreme temperature variations without degrading. By late 1912, the accumulated refinements transformed the Vickers from a promising prototype into a production-ready system. The final curiosity that explains the Vickers design philosophy emerged not during initial development, but during an extended demonstration conducted for evaluation committees. Engineers had loaded 10,000 units of ammunition and filled the water jacket to capacity. The test protocol specified continuous operation, no pauses, no adjustments, no maintenance, until ammunition was exhausted or the system failed. For the first several thousand cycles, operation proceeded as expected. The toggle lock cycled rhythmically, spent casings ejected in a steady stream, and the canvas belt fed without interruption. Steam rose continuously from the condensation canister as the cooling system converted thermal energy into phase changes. But around the 7,000 cycle mark, observers noticed something unexpected. The device's rate of operation had increased slightly. This wasn't a malfunction. Careful measurement confirmed that the Vickers was cycling faster than at the beginning of the test. The explanation revealed a fundamental characteristic of how thermal expansion affected the entire system. As components heated and expanded, clearances between parts decreased. Tighter clearances meant less mechanical slop. The barrel and bolt assembly recoiled more crisply, springs compressed more efficiently, and the toggle lock broke and reset with slightly less wasted motion. This thermal optimization was unintentional. Maxim hadn't designed the device to speed up as it heated. But the phenomenon demonstrated that the Vickers design had achieved something remarkable. The thermal expansion that compromised other automatic systems actually improved this one's operation within its designed thermal envelope. The water jacket prevented temperatures from exceeding safe limits, while the precision of component tolerances meant that moderate thermal expansion optimized rather than degraded performance. The test continued beyond 7,000 cycles. At 8,000, the rate of operation stabilized. The system had reached thermal equilibrium, heat generation exactly balanced heat dissipation through the water cooling system. From this point forward, the Vickers maintained absolutely consistent operation. Each cycle was identical to the previous one. The mechanical rhythm became so regular that engineers could predict exactly when each unit would cycle based solely on elapsed time. At 10,000 cycles, the ammunition was exhausted. The device was still fully functional. Inspection revealed no damaged components, no excessive wear, and no signs of impending failure. The barrel showed discoloration from heat exposure, but dimensional measurements confirmed it remained within specifications. The toggle lock mechanism, which had cycled 10,000 times under extreme stress, showed only minor wear on contact surfaces. Wear that would require hundreds of thousands of additional cycles to approach failure thresholds. This demonstration proved what Maxim had theorized. A properly engineered automatic system could sustain operation indefinitely with only periodic water and ammunition replenishment. The key wasn't just cooling the barrel, it was designing every component to operate within a thermal envelope where expansion was beneficial or neutral, never destructive. Observers recognized the implications immediately. Previous automatic systems were specialized tools, useful for brief periods, but requiring frequent rotation and extensive maintenance. The Vickers was an industrial tool capable of sustained operation comparable to factory machinery. This distinction transformed how strategists conceived of logistical power. With the Vickers, a single position could deliver continuous output for hours, fundamentally changing the mathematics of defensive arrangements. The final curiosity wasn't a single component or clever mechanism. It was the system-level thinking that accepted thermal constraints as design parameters rather than problems to be solved. The legacy of the Vickers machine gun extends far beyond its immediate applications. The system established engineering principles that influenced automatic design throughout the 20th century and continue to inform how engineers approach systems operating under thermal stress. What made the Vickers significant wasn't its primary purpose. Many devices could perform similar tasks. Its significance lay in reliability under sustained operation. This seemingly simple requirement demanded solutions to problems that crossed multiple engineering disciplines: thermodynamics, metallurgy, mechanical timing, fluid dynamics, and material science. No single brilliant innovation made the Vickers successful. Success emerged from the integration of dozens of incremental refinements, each addressing specific constraints revealed through testing. The water cooling system in particular represented a design philosophy that accepted weight and complexity as reasonable trade-offs for sustained operation. Later designs would move toward air cooling and quick-change components, seeking reduced weight and simpler maintenance. But these designs inherited the Vickers' fundamental insight. Thermal management must be integral to the design from the beginning, not added as an afterthought. The toggle lock mechanism influenced subsequent recoil-operated designs, though few later systems retained the exact geometry Maxim developed. The principle of using recoil energy to operate the mechanism became standard across countless automatic systems. The specific timing relationships the Vickers established, when to unlock, when to extract, and when to eject, provided baseline parameters that designers referenced when developing new systems. Perhaps most significantly, the Vickers demonstrated that industrial-level reliability was achievable in portable automatic hardware. Before 1912, automatic systems were experimental curiosities prone to frequent malfunctions. The Vickers proved that appropriate engineering could create systems as reliable as any factory machinery, capable of operating for extended periods without failure. This reliability transformed these mechanisms from interesting possibilities into essential equipment. The device remained in service for decades, seeing use in various capacities well into the late 20th century. Its longevity testified to the fundamental soundness of the engineering principles it embodied. While the specific implementation became obsolete as materials science and manufacturing techniques advanced, the underlying approach, careful attention to thermal management, precise mechanical timing, and system-level integration, remained relevant. Modern automatic systems reflect lessons learned from the Vickers development process, even though they employ different cooling methods and operating mechanisms. The discipline of thermal analysis, the importance of testing under extreme conditions, and the recognition that sustained operation imposes constraints different from brief sessions. These insights trace back to the systematic engineering work Maxim conducted. The 1912 refinement represented a moment when engineering rigor caught up with mechanical ambition. The result wasn't merely a piece of hardware, but a demonstration that complex, highly stressed mechanisms could operate reliably if designers understood and accommodated the full range of forces, temperatures, and stresses the system would encounter. This engineering philosophy, designing for the extremes rather than ideal conditions, became foundational to modern development and continues to influence how engineers approach any system that must operate reliably under challenging conditions. If you enjoy calm, true stories about how engineering shaped the world, subscribe to the channel, leave a like, and tell us from which country you're watching.